Hello there and welcome to our next computer science video looking at 1.2.3, which is software development. This is the third video now I think I've done, and I've got one more after this to complete the chapter of 1.2. So in this video we're going to look at understanding the waterfall life cycle, some agile methodologies, extreme programming and the spiral model, as well as RAD or rapid application development. We're also going to look at the merits and drawbacks of different methodologies and when they might actually be used. And then finally, writing and following algorithms, which is probably one of the most vague things they can ever put on a specification, but we're going to look at it anyway. So let's jump straight in. We've got types of software which we discussed in previous videos, but software refers to all programs that run on a computer, and we have two main categories which you're fully aware. We have application software and we've got system software. Our application software is software that fulfills a specific need or performs a specific task, whereas system software is designed to run a computer's hardware and provide a platform for applications to run on top of, like our operating system. So when we get involved in software development, we're looking at a key set of stages. We've got analysis, we've got the design, we've got the implementation of that design, so that's programming, testing and installation, and then we've got the evaluation. Not to forget, after the evaluation has happened, we need to also implement, put that in and maintain it. So how do we actually do each stage of the software development lifecycle? Well, in the analysis stage, you're trying to work out whether something's feasible or doable. There's no point in starting a task if you are going to make a loss on it. There's no point in starting a task if it's actually not even possible to do it because the technology doesn't exist. So there's a person involved in this stage, and it's called the systems analyst. And what they do is they gather information about the current system, their processes, what the new system needs by conducting interviews and questionnaires. And they might even sit in your building and do some observations of people using an existing system. Or you can also have a look at existing documentation to see what kind of processes are being done by your system currently. And the systems analyst produces a system specification or a user requirement document. And what that does is it defines what the system will do by the end of the development, almost like a checklist. The design stage, the software design stage, will include a description of the data types that we've got, format, the validation that we might need. We also talk about the different database design, and we might put that down into third normal form, for example. We have inputs and outputs, as well as how the data will be processed and stored, and how the data will, how the software will actually be tested as we go along. Now, a lot of people often overlook the design stage, but it probably is one of the most important stages going, because it will actually, the more time spent in design will actually speed up the next stage, which is implementation, because everyone will know exactly what they are doing. So the implementation stage includes coding and testing the software as we go, and it includes a number of different types of testing which we'll cover across the specification in computer science. But we also write user and technical documentation. So user doesn't have jargon in it because it's for the user. It's how-to guides, basically. And the technical documentation is what we provide another developer or somebody that's going to maintain the system. And we've got information about installing the software for the user as well. Now, in the evaluation stage, it's time to find out if everything we did actually worked and compare it against the analysis stage's requirement specification. The user now needs to test every aspect of the software to make sure that it does what it is actually supposed to do. And if it does, tick in the box, I'm probably going to get paid. The software will be evaluated against the original specification document. And this stage is also called acceptance, or we do perform acceptance testing. That's normally with the stakeholder to say, I asked you for A, B, and C, and you provided A, B, and C. Therefore, project is a success. And we'll have a look at testing a little bit later on. So, Finally, once the system is up and running, we need to maintain it in case anything goes wrong. And there are a couple of different types of maintenance that we need to be aware of. And the first one is corrective maintenance. And that is the type of maintenance where we'll fix any errors or bugs discovered in the software after the deployment. Now, in an ideal world, we wouldn't have bugs, would we? But testing isn't a perfect solution. Normally, we'll have users using it in very different ways, and they will come up with issues and bugs, and we'll have to get them and fix them because issues may arise due to unexpected usage scenarios. So we'll get that fixed during corrective maintenance, and then we've got adaptive maintenance. And that involves updating the software to ensure it continues to work correctly in a changing environment, such as new hardware, new software, working alongside it, operating systems. And we need to make sure that the product is still going to work for you regardless of what security patches or what changes we make to a system. So we would make adaptive maintenance changes as we go. And then the third one is perfective maintenance, and that focuses on improving the software by adding new features and enhancing performance, or making the system more user-friendly based on user feedback or changing requirements. A perfect example of this would be something like GDPR that came in under the Data Protection Act. That meant that lots of web products had to change when it came in, and we needed to prepare for that change, and that would be where perfective maintenance is actually brought in. So they're the stages that we're trying to cover in the software development lifecycle. Some, if you look online, there'll be some extras in there as well. That's fine, but these are the core ones that we actually look at. So if we just focus on testing a little bit further, what I'd like you to know is, where do these things actually come in? So if we've got testing called black box testing, black box testing requires no knowledge of the code. And I want you to be clear on that, because it focuses on testing the software's functionality without knowing the internal structure of the code. You can get internal testers working on this, or you can outsource this testing, but you provide a test script, and then someone will sit down with the system or the part of the system, and they'll put in inputs, and they'll look at the sheet and it'll say, okay, you're going to put in the number 2 and the number 2, and it should output 4. If it outputs something else, you would comment on that and say, it outputs this instead, test failed. The next one is white box testing, and it involves examining the internal logic, the structure, and the pathways of the software. Now, it's important here that it's done by the development team themselves, because they are the only ones with the knowledge of every branch in your system. So that's every if statement, every else if statement, every function call, where it can go, what it does in every single scenario and stage. So testers ensure that all code statements, branches, and conditions are executed correctly as we go. Then we move to alpha testing. Alpha testing is conducted in-house by developers still and testers before the software is released to the users, and its aim is to identify and fix major bugs and ensure the software meets the requirements. Beta testing is very commonly known by lots of my students because they might have come across a game that's in beta. This is performed by a select group of real users in a live environment, and it gathers feedback on functionality, usability, and performance to identify issues that are not caught during the alpha testing stage. And what's good here is you can massively expand the net. Lots of companies offer partially working or limited copies of their games, for example, and they would say download it, use it, test it, and then all the information will go back to the development team. Microsoft are a perfect example of this. When they send out their new Windows operating system, you'll get it in beta. It'll be buggy and a bit laggy, and you'll be using it, and you'll get a free copy of it, but you have to report back to the development team, so that's the trade-off. And that saves Microsoft a lot of development time and also cost, because they're using you as the tester without paying you, which is nice for them. Then finally, like I said before, we've got acceptance testing. That's the final phase of testing performed by the end users or clients to ensure the software meets agreed upon requirements, and it's ready for deployment. This is the go, no-go stage for release, and I've seen software that has no-goed. Sometimes you'll see other things as well. There was a classic example of Cyberpunk, if you've ever seen that game before. That was pushed out, and that definitely should have been a no-go for release, but stakeholders pressured the team and they released it, and it was buggy, and it really didn't help the reputation of that game. So make sure you're aware of where these things come in the stages of development. Black box and white box are done before any major releases. Alpha testing is done before any end users see the game or the software at all. And then beta is when the end user might start to see it. And finally, we've got acceptance testing that's done by the stakeholders at the end, or a group of selected testers. Now, we talk about these different methodologies. So methodologies are like a flavor of how you would develop your software. And what you need to know here is why you might choose one over the other. And you might have to argue that case in the exam. So why might you choose a waterfall methodology over an agile methodology, for example? So let's understand the characteristics of each one first. The waterfall methodology is probably one of the older ones, the oldest one, and it's very rigid in its design. So you'll see there you've got analysis, design, implementation, evaluation, and maintenance. And it trickles down one after the other. So the waterfall methodology is what we call a linear and sequential approach to software development, where the process is divided into distinct phases, each completed before moving on to the next. And I'll point out here that you must complete the stage before moving on to the next one. And it's that rigid that it can also mess with your timeline, which is a real problem. It's widely used in projects with well-defined requirements and minimal expected changes. So waterfall is not good for requirement changes. Key features that we have in the waterfall methodology: the sequential progression, so each phase is completed before the next one begins. Documentation driven, so emphasis is placed on thorough documentation at every stage, and this is why the government tend to opt for a waterfall methodology, because they're spending taxpayers' money. They need to document exactly what happens at every single stage. You have fixed requirements, so works best when requirements are stable and well defined at the start. So what's good about waterfall methodologies? Well, they're simple to understand and manage. They have clear deliverables and written documentation at each phase, and you hand over to the next one. You also have they're suitable for projects that are predictable and stable requirements like we talked before, but there are some disadvantages. Because it's so rigid, it's not flexible to changes once the project is underway. So that's why in government lots of these fail, because the world is changing all the time and we can't always adapt as needed to the real world environment. So by the time the software gets produced, it's often out of date, which is a problem. Also, not much user involvement after the analysis stage, so it definitely lacks feedback at each stage. And the counter argument is, why would you need feedback? Because it's so rigid and well designed and well thought out. You wouldn't need feedback. Not always, unfortunately, not always. Okay, late discovery of issues can be costly, because we don't go back, but if we had to, everything's going to slow and basically grind to a halt, which is not great at all. It's unsuitable for projects with evolving requirements or high uncertainty. So the model is suitable when the requirements are very clear and fixed, there's no ambiguous requirements, and technology is well understood. And also, the project is quite short. Not great for long-term projects. And next we move on to the spiral model. And I've put a little diagram down there to show you what the spiral model looks like and where it gets its name from. So the spiral model is a software development methodology that combines iterative development and elements of risk management. And that word risk is going to pop up over and over and over again. You'll always find it in a mark scheme. So the four basic steps that we talked about before: analysis, design, implementation, and evaluation, minus the maintenance stage here, are followed. It is well suited for large, complex or high-risk projects. And the process is visualized as a spiral, with each loop representing a development phase. Each loop builds on the previous one and increases the project's functionality. Iterations continue until the product is complete and meets the user requirements. And there are some key features here. So it focuses on risk analysis and iterative development. It will divide the development into phases, often called iterations or spirals. And it incorporates elements of both the waterfall and agile methodologies, and you'll see all the different methodologies we look at try and pinch certain elements of each other to make them as effective as possible. The advantages here are that we're focusing on risk management, and risks are addressed early and continuously. We try and make sure that the risks are mitigated for as we progress. It's flexible. It allows for changes based on feedback and evolving requirements. There's lots of customer involvement, and that might be a problem, but it might also be an advantage because regular feedback ensures the product aligns with the user needs. And there's lots of early prototyping, and that helps the stakeholder visualize what the system will look like as it progresses and also what it might look like at the end. And also the customer knows that you're moving towards the key requirements that you specified in the analysis stage. There are some problems though. The complexity. It's required for skilled project managers to take over these projects and to manage them effectively all the way through from start to finish. And that's pretty tricky because there's lots of iteration planning, there's lots of risk analysis going on as the project's progressing, and you're trying to tame the project as we go, which is quite difficult. There is a cost associated to this as well because risk management and iterative development can be expensive. And why is it expensive? Because the user might tweak and change things as we go and creep away from the original scope of the project. And that's called project creep, or scope creep. And that's where we move away from the original objectives, and that's going to cost us because we didn't originally plan for doing it in the first place. And those changes are time consuming. So additional iterations may increase development time. We don't know how long it will take us in this case. So this model, the spiral model, is suitable when working on medium to high risk projects and also when users are unsure of their needs and what the possibilities actually are. And that's because the spiral model gives us that flexibility to produce each spiral some version of iteration towards the final goal. And it also, when the requirements are quite complex, because we can keep working on them, chunking them, and then progressing towards the final goal. Also, it's suitable for large projects, as we discussed before, which may take even years to develop, during which time new technologies may develop and significant changes may occur. So because the length of time, the number of iterations, these things can tend to be very costly. After that, we've got one of the most common methodologies on the market currently, and that is the agile model. And with the agile model, you need to keep in your mind the word sprints here. Looping and sprints, iteration and sprints. The agile methodology is flexible. It's iterative in terms of it will repeat and you can go back and do things again. It's not as rigid as waterfall, and because of the iterative approach to software development, it emphasizes on things like collaboration, adaptability, and continuous improvement. Software is developed in a rapid incremental cycle, very short sprints. Each version builds on the previous to add functionality, and each version is thoroughly tested before release. So we're testing as we go. It's good for small time-critical projects with limited planning, and you can basically get started pretty much straight away. And this is why developers tend to like it, because there's not as much focus on paperwork. Now, some advantages. We've got the adaptability, because we can respond quickly to changes in requirements, and there's lots of customer collaboration. They're brought in to advise and to guide us as we're developing. So we do have frequent interaction, and that can be someone's sole job in a software development team, just interacting with the customer and feeding it back to developers as we're going. Also, you've got faster delivery or faster deliverables because it delivers functional software, incrementally reducing time to market. For example, you've seen the explosion of AI. Companies like ChatGPT will rush a product to market even though their product isn't fully formed, and they will capture the user base and they'll start just adding on and fixing and improving in an agile way. Also, you've got continuous improvement. That's regular retrospectives, and they improve the team performance because there's lots of feedback between the team, things to work on, use of specialisms in the team, etc. And that's very good in an agile model. So, what about disadvantages? Sounds good, right? Well, it's less predictable. If you came to me and said, John, I want you to create the software and how much it's going to cost and how long it's going to take. If I was doing an agile model, I'd say I have absolutely no idea. No idea. But we'll start and we'll charge on a monthly basis, for example. It's hard to estimate the cost, the time and effort up front. We'll do that as we go. It requires discipline. Teams must be self-organized and maintain close communication, which developers aren't always very good at. You have scope creep. That was what I was talking about before, where constantly evolving requirements can lead to uncontrolled growth of your project or new requirements coming in that you didn't plan for. And this model is suitable when new changes need to be implemented. Small incremental changes can be made frequently and for little cost. In an expanding or developing business where users' needs are continually changing and developing. So, what about extreme programming? Sounds interesting, doesn't it? Extreme programming. I've got a diagram there, and you'll see there's arrows spinning off the main outer circle. We have things like iteration plan, acceptance tests, stand-up meetings, pair negotiation, unit tests, pair programming, code, release plan. And we go back and we start again. And you'll notice that there's times in between them. So extreme programming is actually a version or a derivative of agile development. That's right. It's a child of it, let's say. So it's designed to improve software quality and responsiveness to changing requirements. And we know that Agile works in phases. So extreme programming does the same. It emphasizes frequent releases, close collaboration, and technical excellence through a set of specific practices and principles. So this is more focused on the developers themselves, how they do it, how they produce high quality software at a very quick pace. So what can go wrong with that? Well, you've got people moving out. You might have a really experienced and a genius on your team, and then they get a job somewhere else and they disappear. That's a problem because the speed in which we're working, if somebody leaves halfway through, that's going to hurt. So personnel change. We might have requirements change on us that require the whole team to move and change direction at a very short notice. And while we're developing, we might even have technology changes. So advancing technology might mean that the software or the hardware we were using is now a better version. We need to shift and develop for that instead. And also costs can spiral. Because the focus is on the development team, they're not really bothered about the cost of the project. As long as they get paid, they don't care. Okay? And as we go, just don't forget that any project can get cancelled and that can scupper what you're trying to do. So this model, extreme programming, is suitable when there's projects with rapidly changing or unclear requirements. Also, it's suitable when teams are seeking to improve code quality and maintainability. So yes, that means you can pick up an existing code base and go for improving it. Also, it's suitable when collaborative environments are there with strong customer involvement. Next, we've got rapid application development. Now, RAD is very highly regarded in the programming world because the focus is on getting stuff done. However, the only drawback to that is there's a degree of testing involved as well. So trying to be dynamic and trying to be quick here is the aim of the game. Rapid application development is a software development methodology focused on speed and flexibility. So it emphasizes iterative development, user involvement, and quick delivery of functional components. There are a number of key advantages here, and you can be the judge whether the advantages here outweigh the disadvantages. So the first one is we've got a faster delivery of functional software. That's good. That's good. That's what we want. High adaptability to changing requirements, and that comes from the user feedback. And we get that all the way through to the point where you'll be sick of the customer because they're constantly chirping in your ear about what should change. We like that, we don't like that, that will work, that won't work. And what that does is, because the user's there all the time, and because we're doing lots of testing, and because we're going back, we might even go back and revisit something, we've got frequent testing and frequent iteration, always moving towards the objectives that are ever changing and the goals. So, what are the problems with it then? It's not suitable for large, complex systems requiring extensive documentation. No way near enough documentation goes on in this stage. Nothing like the waterfall methodology. It requires active user involvement and also quick decision making, and that might compromise the quality if the speed is prioritized over thorough testing. And because of that, I've seen software that's been released that is really not that good in terms of its testing, its buggy nature, and that can have a lasting impact on people's perception of a company or even the perception of my development team. So when is this suitable? When do we use rapid application development? Well, you're going to use it when projects have tight deadlines. You're trying to rush to market. Again, we bring up the AI explosion going on at the moment. Okay, now systems require frequent updates based on user feedback. The world is changing so rapidly, this allows us to keep up with the pace of changing technology or changing customer requirements, I suppose. So environments with clear objectives and available user input will work well with rapid application development, and it's best for dynamic projects. And you might have heard of that word before, dynamic. That is our data structures. They're dynamic because they adjust to changing requirements, and just like rapid application development, it's the same. All right, where speed and user satisfaction is critical. Next, we look at writing and following algorithms. We are done with our methodologies now. We're looking at writing and following algorithms, and I wish exam boards would just listen, because they're so woolly and vague in this area, but it's one of the most difficult stages for students to master. I don't always think it's the student's fault here, by the way, but it takes practice. So, quick recap. What is an algorithm? An algorithm is a set of instructions to solve a problem or complete some well-defined tasks in a finite number of steps. Okay? It's the steps taken to solve a problem, if you like. Now, types of problems solved by algorithms are things like routing problems in networks and packet switching. We've got timetabling problems, searching for numbers in arrays and lists. We've got encryption of data, sorting algorithms in ascending and descending order, and even writing a basic compiler. These are all problems that get solved by algorithms, people. So, what about a good algorithm then? When writing an algorithm, we use pseudocode. Pseudo meaning fake, right? Fake code. It's a high-level language. The good news is here, there is no accepted convention for pseudocode, as long as somebody reading your exam can understand what you're trying to do in terms of the algorithmic content. You will still achieve marks no matter how you write it, okay? But it is a semi-English structured language, There are different exam boards give you prerequisites or things that you would write and how they want it written. But it is just so confusing. Just agree on something, okay? But we need to ensure that our algorithm has a clear and precisely defined a set of steps that produce the correct output for any valid set of inputs. So we should allow for invalid inputs. We should tell the user if something's not right, and output messages correctly, and meaningful outputs are always important. It must always terminate at some point and finish. It should perform the task efficiently in as few steps as possible, but it's not always possible that. It should be designed in a way that other people will be able to understand and modify it if necessary. So that's a good algorithm. Now in your exam, students often ask me, how on earth do I learn? How on earth do I learn these things? Well, there is a series of videos on my YouTube channel which take you through pseudocode problems, and for different exam boards. It really doesn't matter, people. It really, really doesn't matter. OCR have an exam reference language interpreter, which I don't. It's okay. It just tends to add more confusion, but it's like writing code, really, but not real code, which is interesting. The AS specification doesn't require you to do programming as such, but you know, I think you're getting the gist here. If I just if you go to this here, OCR exam language interpreter, you can see here at the top you've got home, about, examples, docs, licensing, all that stuff. Just have a look at the examples on here, and choose one of them. There's a password checker. There you go. You can see it's got a function, validate user. It's not Python, but it kind of is, but it's missing bits. You've got constants, a do until, that's iteration. You've got return values, ending functions here. So we do, in pseudocode, we do end things like if statements, for example, which we wouldn't do in Python. Elif in Python, but else here. You can run this. So when you're writing it, you can run passwords. I need a password check, but it just works out what your attempts should be, really. And then checks it. So if you keep going, there you go. Program ended with a no. Okay? So that is the OCR language reference interpreter, if you like. So while we're talking about practice, let me model some practice for you. Here is an example exam question. If you feel like you can have a go at it straight away, pause the video and have a go then. I will do it. So, you know, if you're stuck, you can play it and watch me do it. A programmer is going to design a procedure that will prompt for and receive two values. So it's going to receive input, two values, A and B. The procedure will then compare them. Compare. That's what it looks like in Python, a comparison symbol. The procedure will also write a suitable message. So that's some kind of output. To a file, well, that can be tricky, on disk, depending on whether. So if the values are the same, A is less than B, or B is less than A. Okay, notice how it says less than. It doesn't say less than or equal to, does it? Very important that you point that out there. Use pseudocode to write the procedure. So the first thing I need to do is read in what A and B is. And that'll get me some marks on the board. So let's declare a variable called A, and let's declare a variable called B, and we're going to say, use the keyword input. Okay? Input. Now I'm going to put my message in a set of brackets. So this is the message that the user would see. And I will say, enter value A, close bracket. And it's the same process for B. So equals is an assignment operator. And when you read code, read from, I read right to left. So what this is saying is, ask the question, get the user to input something, and then assign it to the variable A. Okay? That's how I read in my strange brain. Value B. Speech marks closed. There we go. So that's going to get you some marks already. And then what it does now, we've got to check now and look at the different conditions. So we've got the values are the same. A is less than B. Or B is less than A, that says. So let's do some comparison then. So we're going to say, let's do... Okay, we'll choose one of these comparisons first. I'm just thinking here, the values are the same. I could check if they're the same thing first, but I could use an else for this. So I'm going to say this is going to be my else statement. So if all else fails, we're going to check that they're the same. If A is less than B, do something. Else if, I need another comparison, another condition. I'm going to say B is less than A here, and then my else is this one. Because if it's not less than if A is not less than B and B is not less than A, then the assumption is they must be the same. And that's what the else is for. All right. Some students could put an else if there doing a comparison, but you are wasting an else if really. But there we are. Now, how does the last bit there write a suitable message to a file on disk? Okay, so to do this, the file handling, let's make a variable called my file. And just remember with the file handling, one, you've got to open. Two, do something. So read, write, or append to a file. Read, write, or append. That's W, R, or A. And then you've got three. Make sure you close that file. Good practice, people. Good practice. So if A is less than B, I've got my file here, and I'm going to say, right, stage one, we need to open the file. Now in OCR, this is what they specify in the specification. Open write. I'm just going to call it output.txt. There's my text file. You could put anything in there if you wanted to, as long as it resembles some kind of output. Don't have to be output.txt, but I've used the command word open write because we're going to open it in write mode. So I'm going to put something in it, and my file is the reference to that external file, which means now I can say, well, my file dot keyword now again, write line keyword, and then you put your suitable message in here, which is A is less than B. And then you've got down here, same thing, my file dot write line B is less than 8. And then else, in the else part, same thing again, but this time your message is just going to be that they're the same. Okay, pseudocode, we end ifs in pseudocode and end iteration as well. So selection and iteration gets ended. And then don't forget, stage 3, close the file, and that is my file dot close, and it is a method, so we will close it there. All right. 5 marks for that, 5 marks for that. Where do the 5 marks come from? Well, you've got your A and B being read in there will get you 1 mark. You've got the correct comparisons, so these 3 in here, the comparisons will get you 1 mark. That's 2 so far. You've got the correct output messages, so correct output messages in there. That will get you 1 mark. And you've got the open file, because you're doing file handling. That will get you 1 mark. That means we're up to 4 here, okay? And then you've got the right 2. So the right lines, right lines, right lines, and the close. That gets you that mark. And this is why people always lose marks with file handling, because they always forget to close the file. Believe me, I've done it myself. I have done it myself many times. So there we are, 5 marks for that one, people. All right. So if you're not sure, pause the video, have a go yourself, but practice, practice, practice. All right, let's have a look at this dry run exam question. Here's our trace table. This is a proper exam question. We've got a 3 marker and a 2 marker, and the procedure below manipulates a past integer value and gives a single or multiple output. Procedure, there's some code. Procedure change integer as a parameter called value integer. We've got some variables on that line over there, that line. We've got a repeat until, so a post condition loop there. We've got some code in between here with lots of assignments, it looks like. An output, and then an output here, and an end procedure. It says, for example, change integer 1234 would output 4321 plus. So it reverses this and puts a plus on the end. Complete the trace table for the following procedure. Call change integer 4082. So I'm expecting this algorithm to output 2804 with a plus at the end, because that's what happened there, right? Now, in your trace table, any changes that go in here are added, but only if changes happen. So what I would do is I would start by looking at this, taking a pencil to my exam and saying procedure, change integer, and I would remove this line here, and I would replace it for 4, 0, 8, and 2. Okay. Remember, there's no calculators in the exam, so the calculations can't be that difficult, surely. Integers are created, so we've got p, x, and m. They are variables, p, x, and m. And it says output there. Now, I've entered the value in as a parameter, so I know that this here is going to be 4082. And I've got a loop. So as I have now completed this line and created the variables in my trace table, the repeat starts off with p. P is given the value of value div x. So you take the value, which is 4, 0, 8, and 2, and you divide by 10 and keep the whole number. A div operation divides the number by the required number here, which is 10, and only gives the whole number integer. A modulus operator will do a division with the number provided, but it will only keep the remainder of the division. It doesn't keep the whole numbers. So div is whole numbers. So if I divide that by 10, it's going to give me 408.2. And I get rid of that because there's no integers, no remainder to my division. So I know that P is going to be 408. And then it moves to the next line. X equals P multiplied by 10. So what is 408 multiplied by 10? Well, that's 4080. Then it says M is the value 4082 minus X, which is 4080. And if you take them away from each other, you'll be left with 2. Okay. Then we output whatever the M value is. So M gets outputted, and that is 2. There we go. So that's a good start, isn't it? It's done that bit first. Excellent. Then it says we've outputted M, 2 gets outputted, and then value equals P. So value is now whatever P is, and P is 408. Now we check the condition to end the loop. until the value is less than or equal to 0, we keep looping. So until 408 is less than or equal to 0, keep looping. Okay, well, it's definitely not, 408 is definitely not less than or equal to 0, so stay inside the loop. And we go to and repeat this line of code here. So P is given the value is 408. Let me write that down. 408 div 10. What does that give us? That gives us 40.8. Get rid of the division remainder, and that means P is 40. X equals P multiplied by 10. I can do that. I can do that maths. There you go, 400. And then M is value. So 408 minus 400. And that leaves us with 8. Output M. 8 gets outputted. Happy days. Value equals P. So that means my value is now 40. Wonderful. Then, value equals P, that's 40. Yep. Until value, so 40, is 40 less than or equal to 0? 40 is not equal to or less than 0, so we must loop again. P equals value, so 40 div 10, that's 4.0, scratch the 0.0, P is now 4. P multiplied by 10, that goes to 40. Wonderful. And then it says M equals value minus X. So 40 minus 40, and that gives us 0. Okay. Output M. That's done there. 248. Sorry, 280. There we go, 280. Don't know why I said that. Weird. Output, done. Output M, and value equals P. What's the value? P is 4. 4 goes in there. Okay. Now, is 4 less than or equal to 0? Nope. So we've got to stay in the loop. P equals value. Value is 4 divided by 10. That gives us 0.4. Scratch. That means P is 0. P is 0. What is 0 times 10? Well, you and I both know that's 0. So that gets, X gets 0, and then we say M equals the value minus X. Value minus X. So value is 4 minus X, which is 0. So 4 minus 0 is just 4. And that's done. And then it says output M. So we output the number 4. Wonderful. Wonderful. Then value equals P. What's P? P is 0. So 0 goes in there. Happy days. And then, so we keep looping until value is less than or equal to 0. Well, 0, value is less, okay, value is less than or equal to 0. So we finish. Loop is now finished. Students think we've finished there. No, we have not. Output. Output plus. So along here, the output of this line will have a plus there. And we've done the 2804, and we've done the plus part now. Excellent. Wonderful. And then it says end procedure, and we're finished. That's 3 marks there, and that might not seem like a lot of marks for what we've just done because of the amount of brain power required. However, you got to stick with it. If you can do this and you can take your time and you breathe, you will get full marks on those questions. Okay? So what I'd like you to do is have a go at the next one. Complete the trace table for change integer minus 243. pause the video, have a go, and I'll put the answers on a screen in just a second. And there's the answers for that question that you've just attempted. Well done if you got it right. If not, go back to the drawing board and try again. Don't be disillusioned. You must keep trying. You will get it. Just takes time. Everyone gets it at different stages, so keep going. Okay, that's us. We're now finished on 1.2.3. If you want to practice your pseudocode or you want to practice your drive running, go and have a look at my YouTube channel. We've got plenty of videos out there covering lots of different things. The next video, we're going to look at the final stage, which is types of programming language, which is 1.2.4. And I cannot wait for you all to join me for that video. I'll see you soon.